Hello everyone, my name is Joe Scorson, channel is called Ethernet Wink, and in today's video, this is the second to last video about options for the Quant Finance Advent code I'm doing. And this is also probably going to be the most detailed video about options that's going to be in this series. Yeah, I think it's going to be a ton of fun. Right after this, the next options video will be mostly about visualization, and then we're going to be getting into the data structure side of things, like with async cache, and with a backtesting engine that we're actually going to be building on that backtesting engine for a pretty big portion of it. But yeah, as always, with every video, the code will be in the description. This is my business X, so thank you guys for getting me above 100 followers on that already. If you guys follow this, you'll get all the updates on here first, and you'll be notified whenever I hop on spaces and trade with a bunch of awesome, super good traders. I have an indicator in collaboration with LuxAlga. So if you guys like to actively trade on TradingView, you guys could subscribe to this and get it on your charts. There's a bunch more details here, and there's videos about on my channel about it. With that being said, that's my face again. I don't want to show you guys that. I want to show you guys this. With that being said, let's get into today's code, today's information. So our task is to add to the previous task by pricing a chain of call and puts. Pricing a chain of call and puts can move the strikes by 1 for simplicity. Also calculate the Greeks and estimate implied volatility. Print out each contract's attributes. Cool. So this is all I got right now for you guys. It's just a main, our get data function, and then I have the Black-Scholes right here. I one-lined it, but just there is the if with the if it's a call or not. So just But yeah, we're gonna be going through like this with the Control Z again, because if we don't, I think that we're gonna be here all day with me typing it out. And also, I think I'd lose some of my explanation in just trying to not have a typo. But we're going to start off with a object for a contract. And there's going to be a bit of simulating going on here, a bit of like, this is what is kind of happening. So that's why we have this market price right here and this premium as two different things. We're going to get into that a little bit later. The first thing that we're going to do is we're going to get a find implied volatility function. It's going to need a market price, a spot price, strike, risk-free rate, days to expiration, and if it's call option or not. Next, in that function, we need a few variables. We need our initial guess for volatility as sigma, how close we can get to it, so it is pretty damn close, and how many iterations we want. To estimate our implied volatility, we're going to be using the Newton-Raphson method. And we're going to get into that actual step later on. But before we do that, we need to get the price of the call option with our spot price and just all these other inputs. Then we need to get the D1, so that way we can calculate Vega. This is the first look at Greeks that we have. Vega is the Greek that represents how sensitive the contract is to changes in implied volatility. After we get that, we could then complete this and go through our Newton-Raphson step. So if we're already below our tolerance, like we're good, we made it, so then we could just break and return. If not, we need to continue it with this step. This step is the Newton-Raphson step. We need to add to sigma the market price minus the price over Vega. And that's how we find the implied volatility. We go backwards to find implied volatility. You have that initial guess, and then you try to get as close. You use that guess to get as close to the price of the option, because the market price is options. It doesn't matter if the price of the option is $1. If someone's willing to pay 10 for it, then all of a sudden it's worth 10. That goes for everything. With that being said, let's hop into another function right here, because we're going to get an actual option chain. Right, so we have Black-Scholes option chain. Now what this does is this will return to us the actual a list right here of contract objects as our option chain, right? So if we keep on going through, we're going to go by 1, like we said earlier. So let's write this right here, right? If we start at 100, we're going to go from 95 to 105 as our strikes. Expiration will stay the same. And yeah, that's that step right here to change our strike every time. And we go through and we find out everything. You'll see why we have to calculate D1 and D2 here. This is just for calculating the Greeks later on. But yeah, then we just get our premium by our Black-Scholes function or whatever pricing model you decide to use. Then we can go through and we can get our intrinsic value. That's just a contract attribute, so we'll set that. So if the spot price minus the strike is I don't want to say this. If that is positive, then we actually have intrinsic value, right? If the strike price is 100 and our spot price is 105, we have $5 of intrinsic value, and then the opposite for puts. I don't know why that was so hard for me to get out. Then we're going to go into start pricing out our Greeks, or calculating the Greeks. So delta is done like this, and it is a measure of how sensitive the contract's premium is to changes in the underlying price. It's also a measure of how likely the market thinks it will expire in the money. So a delta of 0.5 is a 50-50 shot. Gamma is the Greek that represents the sensitivity, the contract's premium's sensitivity to changes in delta. Theta is our time decay. How much does this contract depreciate just for existing? Vega is the measure of how the contract premium will change as volatility changes. Take a little sip of espresso. And rho is the Greek that represents how the contract's premium will change as as the risk-free rate changes. So now let's get into this fallacy of the market price and the premium price, right? So markets are noisy. Markets have a lot of noise, and sometimes some very noisy people have a lot of money. So they make changes in the markets. So we're going to simulate that noise just with a random number. All right, just a random Gaussian distribution. Mean is 0, or mu average, whatever. Oh, mu is 0. Mu is the mean, and sigma is the standard deviation. There you go, it's right there. So we're going to start at 0, and we're going to have a pretty small one. The tickle in my throat needs water, not espresso. That is better. So now we can find the implied volatility using that market price, right? Added to the premium, and our spot price and the initial guess for volatility in here. Because we already did the premium we already have our premium, right? We don't need to recalculate premium. Well, we do, but you know what I mean. Then we can just append the chain with all those attributes and return the chain. So now we can hop into our main, initialize all of our variables, 30, implied volatility of, so 30 days to expiration, implied volatility is 0.2, risk-free rate 0.5, and then so that way we have whole numbers, I'm rounding it down, and yeah. Then we get our chains, then we can just print it out. So let's take a look at what that looks like. So I'm just gonna make my terminal huge. I'm gonna put it below my face though. Made that mistake before. And we're gonna get a ton of information here. Here we go. So let's scroll up to these calls right here. So let's talk about this, the changes in the difference between the option price and the market price and our implied volatility. Because you'll see that initially we priced the option with a 0.2 implied volatility, but here we have a 0.17. And the market is pricing this option way below what it's actually worth. If you could make a model to actually do this in real time with markets, you'll make a lot of money if you're right. If you're right in your forecast and implied volatility, that's all that would need to change. Is all that needs to be different. We say all, but it's a difficult thing to do. So how does this happen in the real world? Because this is obviously an extreme example, and it's also a fake example. It could only exist in this file right here, right? So in the real world, if you could find a contract, if you could find a scenario on a stock where the market is pricing in, market expects very little volatility, right? If you could find that scenario. And so then when you look at the contracts, they're priced pretty cheap compared to what they could be priced at. Maybe this is only 30 cents, but still. What you could then do is buy that contract if you think that the market is undershooting the implied volatility. This happens on a smaller scale with the numbers. But the market's right pretty damn often. The market's wrong pretty damn often. Everybody's wrong pretty often. You know what I mean? There's nothing wrong with that. Part of the game. But this is code to kind of outline how the differences could be, even right here. And it could also go the other way. Could know when not to trade something. Last week when I was trading on Spaces, last Friday, I just took one trade on Tesla. I was right about the direction. I bought calls. It was my setup through and through. It's like you have to take your own setups. You know what I mean? So I saw my setup. I took it. Took a call on it. Trendline breakout with my algo, the one with Lux algo in Confluence. I was right about direction, but I lost money. Why? Well, I bought a 0 DTE. First mistake. But that contract was 92% IV. Right? If Tesla moved really quickly and moved a lot, that contract would have banked. But it did not. So even though I was right about the direction, it took a little bit longer. So the contract appreciated. It just kind of died. If I were to simply just go to the next strike, it would have had less juice in it, just from the, not the next strike, the next day to expiration, which was still close. The contracts would have still been accessible. That contract would have way less juice in it, and I would have been able to make more money because I would have been less likely of overpaying, or I would have overpaid less. That's another scenario where you could use this. The whole idea about pricing options is that there will be this big error, and then it'll snap back. So that's kind of the whole concept I wanted to outline for you guys in this video, where we actually go through and we use a technique, in this case the Newton-Raphson step, to estimate implied volatility. So now you guys know how volatility is actually priced out when you go onto whatever you're looking at, you see implied volatility. You actually know that, oh, okay, so we price out a contract, then the market trades this contract around, and then we see what that price the market trades it to is telling us about how the market expects volatility to go. And then you could decide, are they right or are they wrong? And you could trade according to that. Hope that you guys enjoyed this video. Hope that it was insightful. It's day 7. We got one more video about options. It's mostly visualization because what we were just looking at sucked. But yeah, I hope that you guys enjoy this video. Hope to see you guys in the next one. Advent to Code is still just starting. Christmas is in less than 20 days. That's wild. Hope everyone has a nice, safe holiday. But yeah, I will catch you guys in the next one. Goodbye.